Welcome back to Whispering Universes, where tonight we journey to the most Earth-like world in our solar system, and yet one of the strangest places we have ever encountered. Imagine standing on a beach unlike any on Earth, where the sand beneath your feet consists not of silicon dioxide worn smooth by waves, but of organic particles, the building blocks of life itself, accumulated over millions of years. Before you stretches a lake, its surface mirror smooth, or perhaps gently rippled by a cold wind. But this is not water lapping at your boots. This is liquid methane and ethane hydrocarbons that on Earth exist only as natural gas, here condensed by cold so profound that water becomes as hard as granite. Above you, the sky glows a perpetual orange, thick with a haze of organic molecules that scatter the feeble sunlight filtering down from nearly 1.5 billion kilometers away. The sun itself appears more than 100 times dimmer than on Earth, creating a twilight that never ends, never brightens to day, never darkens to true night. Behind you, when the haze clears, Saturn hangs in the heavens, its rings casting shadows across cloud bands that dwarf our entire planet, a reminder that you stand on a moon, a satellite of a giant world that itself orbits in the cold outer reaches of our solar system. This is Titan, Saturn's largest moon, the only place beyond Earth where stable bodies of liquid exist on the surface, the only world we have discovered that possesses a complete hydrological cycle like our own, though one that operates with methane instead of water. Here, methane rain falls from methane clouds, flows in methane rivers, pools in methane lakes and seas, then evaporates back into the thick atmosphere to begin the cycle anew. The chemistry here resembles what scientists believe Earth might have looked like billions of years ago, before life transformed our planet, before oxygen filled our atmosphere, when organic molecules accumulated in ways we are only beginning to understand. Tonight, here on Whispering Universes, we explore this extraordinary world in detail, tracing how we discovered Titan's lakes, understanding the physics and chemistry that allow liquid hydrocarbons to pool on its frozen surface, examining the weather systems that transport methane from pole to pole across seasons that last more than 7 Earth years, and contemplating what this strange moon might teach us about the possibilities for life in the cosmos and the history of our own planet. We will stand on imagined shores, feel the gentle tug of Titan's weak gravity, watch methane rain fall in slow motion through the thick atmosphere, and wonder at the alien beauty of a world so different from Earth, and yet operating according to the same fundamental laws of physics. The story of Titan's methane lakes begins not with their discovery, but with centuries of mystery, with a moon that stubbornly refused to reveal its secrets, hiding behind the thickest atmosphere of any moon in the solar system. It continues with one of the most successful missions in the history of planetary exploration, a spacecraft that spent 13 years circling Saturn, patiently mapping Titan flyby after flyby, slowly piecing together the story of seas and storms, coastlines and clouds. And it looks forward to future missions, to drones that will fly through Titan's orange skies, to submarines that might one day sail the hydrocarbon seas, to the questions we will ask and the answers we might find on this frozen yet remarkably active world. As we journey through Titan's Lake District, through its methane weather systems, through the implications and mysteries that planetary scientists continue to explore, let yourself drift into the contemplative wonder that this place inspires. Let the strange beauty of liquid methane lakes at perpetual twilight, of organic chemistry unfolding on a world without life, of familiar processes in utterly alien conditions, carry you toward peaceful sleep while expanding your sense of what is possible in the universe. For Titan reminds us that nature is endlessly creative, that the laws of physics can produce landscapes beyond our everyday experience, and that even in the cold, distant reaches of the outer solar system, dynamic worlds await our exploration. The lake is calm tonight on Titan's shore. The sky glows orange. Saturn rises over the horizon. Let us begin. Long before we knew about Titan's methane lakes, before we understood its atmosphere or its chemistry, before we had sent any spacecraft to the Saturn system, this moon existed as little more than a point of light in telescopes, discovered on March 25, 1655, by the Dutch astronomer Christian Huygens. Huygens, using a telescope of his own design, spotted what he initially called Luna Saturni, the moon of Saturn, though it would later bear the name Titan at the suggestion of John Herschel in the 1840s, who proposed naming all of Saturn's moons after the Titans of Greek mythology. Huygens could not have imagined what his discovery would reveal 350 years later, could not have conceived that this distant moon harboured lakes and seas, weather and seasons, chemistry that might mirror the early Earth. For centuries, Titan remained enigmatic, simply the largest of Saturn's many moons, notable primarily for its size, larger than the planet Mercury, the only moon in our solar system with a substantial atmosphere. That atmosphere was discovered in 1944 by the Dutch-American astronomer Gerard Kuiper, who detected the spectroscopic signature of methane in sunlight reflecting from Titan. This was a remarkable finding, suggesting that, unlike our own airless moon, unlike most moons throughout the solar system, Titan possessed something Earth-like, a blanket of gas that might create weather, that might interact with its surface in complex ways. But that atmosphere also created a profound problem for astronomers trying to study Titan. Unlike Mars, where telescopes could discern surface features, or even Venus, where ultraviolet imaging could reveal cloud patterns, Titan presented only a featureless orange disk, its surface completely obscured by a thick haze of organic molecules created by photochemistry in the upper atmosphere. This orange haze, beautiful in its own way, became a veil that frustrated planetary scientists for decades, hiding whatever wonders or mundane landscapes might exist below. The first close-up views came from the Pioneer 11 spacecraft in 1979, followed by Voyager 1 in 1980 and Voyager 2 in 1981. These missions, designed primarily to study the giant planets themselves, made targeted flybys of Titan, returning images that confirmed what ground-based telescopes had suggested: a completely opaque atmosphere that revealed nothing of the surface. Voyager 1, at considerable cost to its ability to visit Uranus and Neptune, made a close approach that allowed its instruments to study Titan's atmosphere in detail, discovering that it consisted primarily of nitrogen, like Earth's atmosphere, with methane as the second most abundant gas, along with traces of hydrogen, argon, and more complex organic molecules. These Voyager measurements revealed an atmosphere thicker than Earth's, with a surface pressure about 1.5 times that at sea level on our planet, and a temperature of approximately minus 179 degrees Celsius. Cold enough to freeze methane into rain and snow, cold enough to make water as hard as granite. The data suggested the possibility of methane clouds, perhaps methane precipitation, raising the tantalizing question of whether liquid methane might pool on Titan's surface in lakes or seas, creating a hydrological cycle analogous to Earth's water cycle, but operating with hydrocarbons. Yet for all these discoveries, for all the data about atmospheric composition and temperature profiles, Titan's surface remained hidden. Scientists developed models suggesting what might exist below the haze, some proposing a global ocean of liquid methane and ethane, others suggesting a dry surface with only occasional rainfall, still others imagining landscapes that might resemble Earth in fundamental ways despite the alien chemistry. But models could only go so far without direct observation, without images or radar maps, without the kind of detailed exploration that would require a dedicated mission, one that would spend not hours but years in the Saturn system, returning to Titan again and again. As the 1980s turned to the 1990s, as Voyager continued outward toward interstellar space, planetary scientists began planning what would become one of the most ambitious missions in the history of space exploration. Cassini-Huygens, a collaboration between NASA, the European Space Agency, and the Italian Space Agency, designed specifically to unravel the mysteries of Saturn and its enigmatic largest moon. The mission would carry instruments capable of piercing Titan's veil, of seeing through the haze to whatever lay beneath, and what it would find would exceed the most optimistic predictions, revealing a world of staggering complexity and beauty. But we are getting ahead of ourselves. Let us return to the moment before revelation, to the years of waiting as Cassini-Huygens made its long journey through the solar system, and prepare ourselves for the discoveries that would transform our understanding not just of Titan, but of what constitutes a habitable world in the universe. On July 1st, 2004, after a journey of nearly 7 years, covering more than 3 billion kilometers, the Cassini-Huygens spacecraft fired its main engine for 96 minutes, slowing itself enough to be captured by Saturn's gravity and beginning an orbital tour that would last until September 2017, far beyond its original planned mission duration of 4 years. Among its many instruments, Cassini carried a sophisticated radar system designed specifically to penetrate Titan's opaque atmosphere, using radio waves that could pass through the haze and reflect off the surface, revealing topography, composition, and surface features invisible to optical cameras. This radar operated at a frequency of 13.8 GHz in the Q band of the radio spectrum, sending pulses downward toward Titan's surface during close flybys and analyzing the reflected signals to build up detailed maps of the terrain below. The technique, known as synthetic aperture radar, or SR, had been used successfully to map Venus through its thick clouds and would prove equally effective at Titan, though what it revealed would be far stranger than the volcanic plains of our sister planet. The first radar images, returned during a flyby on October 26, 2004, showed a landscape of unexpected complexity, with bright and dark regions suggesting different surface materials, linear features that might be dunes or ridges, and circular features that could be impact craters or volcanic calderas. But it was the flyby on July 22, 2006 that returned the image planetary scientists had been hoping for: a dark, smooth region near Titan's south pole, roughly circular in outline, with a bright rim that suggested a shoreline, the first definitive evidence of a liquid-filled basin on another world's surface. This feature, later named Ontario Lacus, after Lake Ontario on Earth, measured approximately 235 kilometers in its longest dimension and appeared remarkably smooth to radar, consistent with a liquid surface that reflected radar waves away from the spacecraft rather than scattering them back. The brightness of its supposed shoreline suggested materials deposited by the liquid, perhaps evaporites left behind as the lake level changed with seasons, or perhaps organic sediments carried by rivers and deposited at the margins. Here was proof that Titan's methane and ethane did not simply rain from the sky and evaporate, but could accumulate in stable bodies of liquid, creating lakes that might persist for years or centuries. As Cassini continued its orbital tour, returning to Titan for close flybys every few weeks, the radar gradually built up coverage of more of the moon's surface, and what emerged was a revelation. Titan's North Polar region was covered with lakes and seas, dozens and eventually hundreds of dark, smooth features filling depressions in the terrain, connected by river channels, fed by rainfall and runoff, creating a lake district that in some ways resembled regions of Earth like Finland or northern Canada, though the chemistry and composition were entirely different. The largest of these features, named Kraken Mare, proved to be enormous, larger than the Caspian Sea on Earth, covering approximately 400,000 square kilometers, with depth estimates suggesting it might contain more liquid hydrocarbons than all of Earth's oil and natural gas reserves combined. To the west of Kraken Mare lay Ligeia Mare, the second largest sea, a roughly triangular body measuring some 420 kilometers in its longest dimension. And beyond that, Punga Mare, smallest of the three named seas, but still larger than Lake Superior. Scattered around and between these major features lay smaller lakes, some just a few kilometers across, others approaching 100 kilometers, creating a landscape where liquid clearly played a major role in shaping the terrain. This asymmetry between north and south puzzled scientists initially, with the North Pole hosting hundreds of stable lakes, while the South Pole showed only Ontario Lacus and a few smaller features, some of which appeared to be dry lake beds. The answer lay in Titan's orbital mechanics and the seasonal cycle driven by Saturn's 29.5-year orbit around the Sun, which creates seasons on Titan lasting more than 7 Earth years each. When Cassini arrived in 2004, it was summer in Titan's southern hemisphere and winter in the north, and the distribution of liquid reflected this, though scientists expected the pattern to shift as the seasons changed. The discovery of Titan's lakes and seas transformed our understanding of the Moon from a place of theoretical interest to one of active, ongoing processes observable in real time. Here was not just an object to be catalogued, but a world to be studied, with weather and erosion, seasonal changes and possibly even tides, a place where the familiar processes we know from Earth operated under alien conditions, where the substances involved were completely different, but the physics remained the same. The radar had pierced the veil, and what it revealed was a world that demanded deeper exploration. But Cassini carried another payload, one that would not orbit Saturn, but would make a one-way journey to Titan's surface, returning the first ground-level images and measurements from this extraordinary world, the Huygens probe, built by the European Space Agency and about to make history. On December 25, 2004, the Huygens probe separated from the Cassini orbiter, beginning a 20-day coast toward Titan that would culminate in the most distant landing humanity had ever attempted. Named for the astronomer who discovered Titan, Huygens was a 319-kilogram spherical probe carrying 6 instruments designed to study Titan's atmosphere during descent and, if it survived landing, to return data from the surface for as long as its batteries lasted. No one knew for certain what Huygens would encounter when it reached the bottom of Titan's atmosphere, a solid surface certainly, but one covered in liquid methane, or dry terrain, or perhaps organic sludge that would swallow the probe on impact. On January 14, 2005, Huygens entered Titan's atmosphere at an altitude of about 272 kilometers, traveling at more than 20,000 kilometers per hour. The entry phase lasted about 3 minutes, during which friction with the upper atmosphere slowed the probe and heated its heat shield to extreme temperatures, protecting the delicate instruments inside. At an altitude of about 160 kilometers, with velocity reduced to subsonic speed, the main parachute deployed, a sequence that had been tested exhaustively on Earth but never before in Titan's thick nitrogen atmosphere. The descent took 2 hours and 27 minutes, far longer than the 2 hours expected based on pre-mission models of Titan's atmosphere, a discrepancy that resulted from atmospheric winds being stronger than predicted, carrying Huygens eastward as it fell. Throughout this long descent, the probe's instruments sampled the atmosphere at different altitudes, measuring temperature, pressure, composition, and wind speed, while cameras captured images every few seconds, gradually revealing the surface below as the orange haze thinned with decreasing altitude. The images showed a landscape that looked hauntingly familiar despite the alien conditions. Drainage networks carved into brighter terrain, resembling river valleys seen from aircraft on Earth, meandering channels that suggested flowing liquid had shaped the surface over long periods of time. As Huygens descended below the lowest clouds, the view became clearer, showing what appeared to be a coastline, a boundary between brighter and darker terrain that could represent the edge of a lake or sea, though the probe's trajectory would take it to a landing site on the brighter, presumably dry terrain. At an altitude of about 60 kilometers, Huygens switched to smaller parachutes to speed its descent through the densest part of the atmosphere, and at 20 kilometers, scientists on Earth, watching data arrive from Cassini as it flew overhead relaying Huygens' signals, could see clear evidence of methane clouds, visible both to the cameras and to instruments measuring atmospheric composition. These clouds represented the active part of Titan's methane cycle, the condensation of methane vapor into liquid droplets that would eventually fall as rain, replenishing the lakes and rivers visible from orbit. The landing came at 11:38 UTC, a gentle touchdown at about 4.5 meters per second survivable, because of Titan's low gravity and thick atmosphere, onto a surface that instruments immediately identified as slightly yielding, like damp sand or clay, with a thin crust overlying softer material. The temperature at the surface read -179.2 degrees Celsius. The pressure 1.467 times Earth's sea level pressure. Huygens had survived, the first and so far only probe to land in the outer solar system, on a world more than 1 billion kilometers from Earth. For the next 72 minutes, until its batteries finally failed, Huygens transmitted data from Titan's surface. The images showed a landscape of rounded pebbles and cobbles, though these rocks were water ice, frozen solid at this temperature, harder than granite on Earth. The darker material between the rocks appeared to be fine-grained organic sediment, the accumulated debris of millions of years of photochemistry in the atmosphere, raining down as particles that covered the surface in a layer that might be meters or tens of meters deep. The view from the surface was exactly the perpetual twilight scientists had predicted, orange sky fading to darker orange-brown near the horizon, the sun invisible through the haze, illumination about 1/1000th as bright as noon on Earth, comparable to twilight under heavy clouds. No lakes were visible from Huygens' landing site, but the drainage channels seen during descent testified to liquid methane falling from the sky and flowing across the surface, carving valleys in the ice bedrock, transporting organic sediment toward lower elevations, shaping the landscape through erosion and deposition exactly as water does on Earth. The success of Huygens vindicated decades of engineering and planning, proving that missions to the outer solar system could not only orbit but land, could not only observe from a distance but touch and sample alien worlds directly. The data it returned would be analysed for years, revealing details about atmospheric chemistry, organic molecules, isotope ratios, and surface composition that informed our understanding of Titan's entire global system. But more than data, Huygens provided something precious, a human-scale perspective, a view from the surface that let us imagine standing on this strange shore, breathing through a spacesuit in the thick nitrogen atmosphere, watching methane rain fall through the twilight, knowing that somewhere beyond the horizon, vast seas of liquid hydrocarbons awaited exploration. To understand how methane can exist as liquid on Titan's surface, pooling in lakes and flowing in rivers, we must first appreciate the precise balance of temperature and pressure that makes this possible, a balance that exists almost nowhere else in the solar system. On Earth, water remains liquid across a range of temperatures from 0 to 100 degrees Celsius at sea level pressure, a range we consider normal because we evolved in it, but which represents a specific set of conditions unusual in the broader cosmos. On Titan, the same principles apply, but with different substances and different numbers. Methane, chemical formula CH4, the simplest hydrocarbon and the primary component of natural gas on Earth, exists as a gas at room temperature and pressure, with a boiling point of -161.5 degrees Celsius at Earth's sea level pressure. To liquefy methane on Earth requires either extreme cold or high pressure, or both, which is why we transport it in refrigerated tanks or pressurized containers. But Titan's surface temperature averages around -179 degrees Celsius, well below methane's boiling point at the pressure Huygens measured, 1467 Earth atmospheres. At these conditions, methane exists comfortably as a liquid, neither frozen solid nor evaporated to gas, occupying the same phase state that water occupies in tropical oceans on Earth. The phase diagram for methane, a chart showing under what combinations of temperature and pressure the substance exists as solid, liquid or gas, reveals that Titan's conditions place it squarely in the liquid region, but not far from the boundaries. A modest increase in temperature would cause surface methane to boil. A modest decrease would freeze it into methane ice, which in fact exists at higher elevations on Titan where temperatures drop slightly below the freezing point. This proximity to phase boundaries means that small changes in conditions can produce dramatic effects, creating a dynamic system where methane continuously cycles between states. But methane does not exist alone on Titan. The lakes and seas contain significant amounts of ethane, C2H6, another hydrocarbon with a higher boiling point than methane, around -89 degrees Celsius at Earth's sea level pressure, which means ethane remains liquid across an even wider range of Titan conditions. In fact, ethane accumulates in Titan's lakes and seas because it is produced in the atmosphere through the breakdown of methane by ultraviolet light and does not evaporate as readily. Over geological timescales, ethane concentrations in the lakes should increase as methane is gradually destroyed by photochemistry and replaced by heavier hydrocarbons. The lakes also contain propane, C3H8, with a boiling point around -42 degrees Celsius, and dissolved nitrogen, which makes up the vast majority of Titan's atmosphere. This nitrogen dissolves in liquid methane, and ethane, like carbon dioxide, dissolves in water on Earth, and changes in temperature or pressure can cause it to come out of solution, forming bubbles, perhaps explaining some of the mysterious, temporary bright features seen in radar images of Kraken, Mare and Ligeia, Mare. The physics of evaporation and condensation on Titan differ significantly from Earth because of the Moon's low gravity, about 1/7 that of Earth, and its thick atmosphere. The lower gravity means that Titan's atmosphere extends much higher than Earth's relative to the Moon's radius, creating a more gradual transition from surface to space. The thick atmosphere means that radiation balance, the interplay between incoming solar energy and outgoing infrared radiation, operates differently, with a greenhouse effect that makes Titan's surface about 10 degrees Celsius warmer than it would be without atmospheric warming. When methane evaporates from lakes or land surfaces, it rises into the atmosphere where the temperature decreases with altitude, eventually reaching a level cold enough for condensation to occur, forming methane clouds, typically between 8 and 16 kilometers altitude. These clouds can grow through the same processes that form rain clouds on Earth, collision and coalescence of tiny droplets into larger ones heavy enough to fall, though the lower gravity means that even large droplets fall slowly, taking hours to drift from cloud base to surface. The resulting precipitation, when it occurs, consists of methane raindrops that can grow larger than rain on Earth before air resistance breaks them apart, perhaps reaching 5 to 10 millimeters in diameter compared to the typical 2 to 5 millimeters for terrestrial rain. These large drops fall slowly through the thick atmosphere, reaching terminal velocities of only a few meters per second, creating what must be one of the most surreal weather phenomena in the solar system: gentle, slow-motion rain of liquid natural gas falling through orange twilight. Once on the surface, liquid methane can flow downhill, pulled by Titan's gentle gravity, carving channels in the water-ice bedrock, which at these temperatures has the strength and hardness of granite. The flowing liquid transports sediment, fine particles of organic material, downstream toward lakes and seas depositing it in deltas and alluvial fans, building up shoreline features that Cassini's radar mapped in remarkable detail. The lower gravity means that rivers on Titan flow more slowly than comparable rivers on Earth, but the thick atmosphere also means less evaporation during transport, allowing rivers to carry their liquid cargo over longer distances. This complete hydrological cycle, from evaporation through cloud formation and precipitation to river flow and lake accumulation, represents the only example we know beyond Earth of a system cycling a substance through different phases on a planetary surface. Understanding its physics helps us appreciate both how alien Titan is and how fundamentally similar its processes are to those we know from home. If we could stand on the shore of Ligeia Mare, the second largest sea on Titan, and could analyze the liquid lapping at our feet, what would we find? Not pure methane, certainly, but a complex mixture of hydrocarbons and dissolved gases, a chemical soup, unlike anything found naturally on Earth's surface, but governed by the same thermodynamic principles that determine how substances mix and separate, dissolve and precipitate, remain stable, or undergo chemical change. Cassini's instruments, though never designed to directly sample Titan's lakes, provided information about their composition through multiple lines of evidence. Radar observations showed that the liquid absorbs radio waves differently than pure methane would, suggesting a mixture with different dielectric properties. Temperature measurements indicated that the lakes do not all have identical thermal characteristics, implying variation in composition between different bodies. And atmospheric measurements showed that methane, produced constantly in the upper atmosphere, must accumulate somewhere, with the lakes being the most logical repository. The current scientific consensus holds that Titan's larger seas like Kraken, Mare and Ligeia Mare consist primarily of liquid methane with substantial dissolved ethane, perhaps 20 to 40% by volume, along with smaller amounts of propane and dissolved nitrogen. The smaller lakes show more variation, with some appearing methane-rich, while others might be dominated by ethane, reflecting differences in how they connect to the global methane cycle, whether they receive fresh methane rain directly or accumulate liquid that has already lost much of its methane to evaporation. The depth of these lakes and seas varies considerably. Ontario Lacus, the large southern lake image during the early Cassini mission, appears relatively shallow, perhaps only a few meters deep across much of its area, though with deeper basins reaching tens of meters. The northern seas, in contrast, show evidence of much greater depths. Ligeia Mare has been probed using radar altimetry and radiometry techniques that suggest maximum depths exceeding 160 meters, comparable to the deeper Finger Lakes in New York State, with an estimated volume of about 9,000 cubic kilometers of liquid hydrocarbons. These depth estimates come from analyzing how radar signals reflect off the lake floor in shallow areas versus how they completely disappear in deep areas, absorbed by the liquid before reaching the bottom. The technique is not perfect and uncertainties remain, but the evidence strongly suggests that at least some of Titan's seas are deep enough to create stratification layers, with different temperatures and compositions at different depths, perhaps warmer and more ethane-rich near the bottom, where pressure is higher and where heavier hydrocarbons would tend to settle. Shoreline features visible in radar images reveal the dynamic nature of these lakes. Some shores appear bright and complex, suggesting deposited material possibly evaporates left when lake levels dropped, analogous to salt deposits around shrinking lakes on Earth. Though on Titan, these would consist of exotic organic compounds rather than salts. Other shores show sharp boundaries between liquid and land, suggesting steep-sided basins carved by tectonic activity or impact events and subsequently filled with liquid. Still other shores display meandering channels feeding into the lakes, river deltas spreading sediment into the calm waters. The surface of a methane lake on Titan should be remarkably calm under most conditions. The low gravity means that even strong winds generate only small waves, and calculations suggest that typical wind speeds observed by Huygens during descent would produce ripples at most, perhaps only a few centimeters high. The thick atmosphere damps wave motion, and the low surface tension of liquid methane compared to water means that capillary waves, the tiny ripples that appear on water even in gentle breezes, would be even less pronounced on Titan's lakes. However, rare strong wind events might generate more substantial waves, and seasonal changes appear to affect lake levels significantly. Cassini observed changes in some smaller lakes over the course of its mission, with features appearing in radar images during northern spring that had not been visible during northern winter, suggesting that seasonal warming drives evaporation from some lakes, while increasing precipitation feeds others, creating a dynamic system that shifts methane from one reservoir to another as Titan's long seasons progress. One of the strangest features of Titan's lakes might be their potential for stratification, not just by temperature, but by composition. As ethane accumulates in the lakes, being less volatile than methane, it should tend to concentrate toward the bottom, creating layers of different density. Dissolved nitrogen, which comes out of solution more readily at warmer temperatures, might create supersaturated bottom layers that could suddenly release gas bubbles, stirring the lake through a process analogous to the catastrophic lake turnovers observed in some volcanic lakes on Earth. If we could sail on Ligeia Mare, we would travel across a body of liquid larger than Lake Michigan, navigating through twilights beneath an orange sky, perhaps encountering the mysterious magic islands that appear and disappear in radar images, possibly floating masses of organic solids or fields of nitrogen bubbles rising from the depths. The shoreline would reveal river mouths feeding the sea, their channels carved through ice-hard water, transporting the organic sediment that gives Titan's landscape its dark coloration. The liquid itself would be crystal clear, not clouded like terrestrial water, allowing us to see downward into depths that might extend for hundreds of meters. This is the anatomy of a methane lake on Titan, a complex chemical system operating at temperatures that would freeze carbon dioxide solid, yet warm enough relative to methane's phase diagram to maintain stable liquid, creating an alien analogue to Earth's oceans and lakes, different in every chemical detail, but similar in fundamental physical behavior. Titan's northern polar region, mapped progressively by Cassini's radar through dozens of flybys between 2006 and 2017, revealed a landscape dominated by liquid, with hundreds of discrete lakes and 3 major seas occupying a total area comparable to all of Earth's Great Lakes combined. This concentration of liquid at high northern latitudes creates what planetary scientists call Titan's Lake District, a region where the interplay between topography, climate, and chemistry produces one of the most distinctive landscapes we have discovered on any world. Kraken Mare stands as the dominant feature, a vast body of liquid hydrocarbons covering approximately 400,000 square kilometers, larger than the Caspian Sea on Earth, the Black Sea, or Lake Superior, Lake Michigan, and Lake Huron combined. Kraken stretches more than 1,000 kilometers from its northern to southern extremity, with a complex outline featuring multiple arms, bays, and inlets that suggest a flooded landscape where rising liquid levels submerged an existing topography of valleys and lowlands. The depth of Kraken remains uncertain across most of its area, with radar unable to detect bottom returns from the central regions, suggesting depths exceeding several hundred meters in places, making it by far the deepest body of liquid known on any world besides Earth. To the west of Kraken Mare lies Ligeia Mare, roughly 420 kilometers across at its widest point, with a somewhat triangular outline and a more uniform depth profile than Kraken. Cassini devoted considerable attention to Ligeia because its size made it amenable to detailed study, while its more compact shape simplified modelling of circulation patterns and seasonal changes. Radar observations revealed that Ligeia's composition is methane-rich, supporting models of active exchange with the atmosphere through evaporation and precipitation, and raising questions about where the ethane produced in the atmosphere accumulates if not in the second largest sea. Punga Mare, smallest of the three named seas at about 380 kilometers in its longest dimension, sits to the west of Ligeia and shows some of the clearest evidence of river inputs, with at least one major channel feeding liquid into the sea from higher terrain to the south. The connection, or lack thereof, between these three major seas remained uncertain throughout Cassini's mission, with some radar passes suggesting possible straits or channels linking Kraken and Ligeia, while others showed what appeared to be land barriers. Understanding whether these seas form a connected system or remain separate has implications for how liquid methane cycles through Titan's northern lake district. Beyond the major seas, Cassini's radar catalogued more than 650 discrete liquid-filled features in the northern polar region, ranging from small ponds a few kilometers across to substantial lakes approaching the size of Earth's Lake Ontario. These smaller lakes cluster especially densely between about 65 and 80 degrees north latitude, creating a landscape where liquid occupies a significant fraction of the surface area, separated by land that radar shows to be relatively bright, suggesting either exposed water ice bedrock or deposits of organic sediment. The distribution of these lakes follows patterns that reflect both topography and climate. Many cluster in what appear to be depressions or basins, suggesting that, like lakes on Earth, they occupy low points in the landscape where liquid can collect. But unlike Earth, where lake distribution reflects primarily rainfall patterns and drainage basin geometry, Titan's lakes also respond to global atmospheric circulation patterns that transport methane vapor from equatorial regions toward the poles, where colder temperatures promote condensation and precipitation. This asymmetry between Titan's northern and southern hemispheres puzzled planetary scientists when first observed, with the north hosting hundreds of lakes, while the south showed only Ontario lacus and a few smaller features, some of which appeared partially or completely dry. The explanation involves Titan's orbital eccentricity. Saturn's elliptical orbit around the Sun means that Titan's southern summer occurs when Saturn is closest to the Sun, making it shorter but more intense, while the northern summer occurs at aphelion, making it longer but milder. This difference produces more evaporation in the south during its summer, drying lakes, while the cooler northern summer preserves liquid that accumulated during the long winter. As Cassini's mission progressed and seasons changed on Titan, with northern spring arriving around the time of Saturn's equinox in 2009, scientists observed changes in the lake district that confirmed this seasonal hypothesis. Some smaller lakes in the north showed evidence of increasing liquid levels, while features in the south appeared to shrink or disappear entirely. These observations, spanning more than 7 Earth years of Titan's seasonal cycle, provided the first direct evidence of seasonal transport of methane from one hemisphere to the other, validating climate models and revealing Titan as a dynamic world where landscapes change over time scales we can actually observe. The morphology of individual lakes varies considerably, with some showing sharp, well-defined shorelines suggesting steep-sided basins, while others display complex dendritic outlines indicating flooded river valleys or irregular terrain filled with liquid. Several lakes show central bright features in radar images, interpreted as islands or shoals, remnants of higher terrain not fully submerged by the liquid filling the basin. The smallest lakes often appear perfectly circular, suggesting they might occupy impact craters or volcanic collapse features, later filled with liquid methane. Standing on a hill in Titan's northern lake district, looking out across this landscape at the height of summer, you would see lake after lake stretching to the horizon, separated by narrow land bridges of dark organic terrain, fed by rivers carrying methane from the last storm, reflecting the dim orange sky in their mirror-smooth surfaces. This is a place where liquid dominates, where chemistry we associate with deep underground petroleum deposits on Earth plays out in open lakes and flowing rivers under an alien sky, where the familiar processes of evaporation and condensation, erosion and deposition create landscapes that echo Earth while remaining utterly foreign. Clouds on Titan form through processes fundamentally similar to those that create clouds on Earth, yet the details differ in ways that reflect the alien atmosphere and exotic chemistry. When methane evaporates from lakes or from terrain dampened by recent rain, it enters an atmosphere already containing methane vapor at various concentrations depending on altitude and latitude. As this methane-enriched air rises, either through convection driven by solar heating or through lifting by weather systems, it expands and cools, eventually reaching an altitude where the temperature drops below the dew point for methane, causing the vapor to condense into tiny droplets around nuclei, perhaps organic particles, perhaps ice crystals of heavier hydrocarbons, forming visible clouds. Cassini's cameras and spectrometers tracked cloud formation and evolution throughout its 13-year mission, building up a climatology of where and when clouds appear, how long they persist, and how they move with atmospheric winds. The resulting picture shows Titan as a world of variable cloudiness, sometimes presenting a nearly cloud-free atmosphere for months at a time, then suddenly developing extensive cloud systems that cover large regions, particularly near the poles, during their respective spring and summer seasons. The altitude at which methane clouds form depends on temperature and methane vapor concentration, with typical cloud bases appearing between 8 and 16 kilometers above Titan's surface, though higher clouds sometimes extend to altitudes of 30 kilometers or more. These clouds appear bright in infrared wavelengths, where methane absorbs sunlight, standing out against the darker background of Titan's haze, allowing Cassini to track their movement and evolution over time. The morphology of Titan's clouds varies from small, scattered features to large, organized systems. Some clouds appear as discrete, roughly circular patches, perhaps associated with convective updrafts, analogous to cumulus clouds on Earth, though driven by weaker solar heating because of Titan's distance from the Sun. Other clouds form in long linear features that might represent frontal systems or mountain wave clouds generated by winds flowing over topography. The largest cloud systems can cover regions larger than Texas, developing complex structures that suggest active weather systems with rising and sinking air, possibly lightning and certainly precipitation. The frequency and location of clouds change with Titan seasons in ways that reflect the shifting distribution of liquid methane between hemispheres and the movement of atmospheric circulation cells. During northern winter, when Cassini first arrived, clouds appeared most frequently in Titan's southern hemisphere, particularly at middle latitudes around 40 degrees south, where the combination of available methane vapor and atmospheric instability promoted cloud formation. As northern spring and summer progressed, cloud activity shifted northward, with spectacular storm systems appearing at high northern latitudes as methane evaporating from the warming lakes fed convective clouds. The relationship between clouds and surface liquid shows up clearly in time-lapse sequences of Cassini images spanning multiple years. Shortly after major cloud systems pass over a region, radar observations sometimes reveal darkening of the surface, consistent with rainfall depositing liquid methane that takes time to evaporate or seep into the porous organic terrain. This correlation between clouds and surface changes provides direct evidence for Titan's active methane cycle, where liquid moves from surface to atmosphere and back again through the familiar processes of evaporation, condensation, and precipitation. One of the most remarkable cloud events observed by Cassini occurred in September and October of 2010, around the time of Saturn's equinox, when a massive storm system appeared in Titan's southern tropics, covering more than 500,000 square kilometers at its peak. This storm produced bright, changing cloud features that persisted for weeks, likely depositing substantial rainfall over a region that had been dry for years. The timing suggested that equinoctial conditions, when solar heating becomes more evenly distributed between hemispheres, can trigger exceptional weather events, perhaps through destabilizing the atmospheric circulation patterns that prevail during the long springs, summers, autumns, and winters. The physics of cloud droplets growth on Titan should follow similar principles to Earth, with tiny initial droplets, perhaps only a few micrometers in diameter, colliding and coalescing through differential fall speeds, Brownian motion, and electrical effects, gradually building up larger and larger drops until they become heavy enough to fall from the cloud base. The threshold for precipitation on Titan is different from Earth because the lower gravity means that drops remain aloft more easily, but the thicker atmosphere means that air resistance eventually limits how large drops can grow before they begin to fall. The resulting rain, when it finally falls, consists of methane droplets that may be larger than typical raindrops on Earth, perhaps reaching diameters of 5 to 10 millimeters before air resistance breaks them apart. These drops fall slowly through the thick atmosphere, perhaps taking several hours to descend from a cloud at 10 kilometers altitude to the surface, during which time they may partially evaporate if they fall through drier air, or continue to grow if they pass through regions of high methane vapor concentration. For someone standing on Titan's surface during rainfall, the experience would be surreal. Large drops of liquid methane falling from an orange sky at walking speed, gentle enough to catch on an outstretched hand, cold enough to freeze carbon dioxide solid, yet at these temperatures perfectly stable as liquid, splashing against water, ice rocks, forming puddles in depressions, trickling into crevices, eventually flowing downhill toward rivers and lakes. The sound would be different from rain on Earth, perhaps quieter because of the lower impact velocity, or perhaps distorted in strange ways by the thick atmosphere's effect on sound propagation. These methane clouds, these alien storms, represent one of the most Earth-like features of Titan, a reminder that the same physics governs weather throughout the solar system, that condensation and precipitation, evaporation and cloud formation proceed according to thermodynamic principles that care nothing for what substances are involved, only for their physical properties and the conditions in which they exist. The first direct evidence that methane rain actually falls on Titan came not from Cassini's orbital observations, but from the Huygens probe during its descent through the atmosphere in January 2005. Instruments aboard Huygens detected methane vapor concentrations that increased sharply at certain altitudes, consistent with falling through regions of active rainfall, or at least very humid air saturated with methane vapor. Later analysis of the descent images showed dark streaks on the surface that resembled wet terrain, suggesting that rain had fallen recently, within days or weeks of Huygens' landing. But understanding the physics of how methane rain actually falls requires examining the properties of liquid methane compared to liquid water, and considering how Titan's unique combination of low gravity and thick atmosphere affects precipitation. Methane has a much lower surface tension than water, about 1/6 as much, which means that methane droplets break apart more easily when they grow large, limiting the maximum size they can achieve. However, the lower gravity and the thick atmosphere create compensating effects that allow Titan's raindrops to grow larger than might initially be expected. When a droplet falls through air or any gas, it experiences drag force that opposes its motion, with the drag increasing as the droplet accelerates, until eventually the drag force equals the gravitational force, pulling the droplet downward. At this point, the droplet reaches terminal velocity and stops accelerating, falling at constant speed. On Earth, typical raindrops reach terminal velocities between 2 and 9 meters per second depending on their size, with larger drops falling faster, but also being more prone to breaking apart from air resistance. On Titan, the calculation becomes more complex. The lower gravity, about 1.35 meters per second squared, compared to Earth's 9.8, means that the gravitational force pulling drops downward is much weaker. But the atmospheric density at Titan's surface is about 4.5 times that of Earth's sea level atmosphere, creating much stronger drag for a given drop size and velocity. When these factors combine in the equations of motion, the result is that methane raindrops on Titan fall very slowly, reaching terminal velocities of only about 1 to 3 meters per second, slower than walking speed for humans, slow enough that you could easily sidestep a falling drop if you could see it coming. This slow fall speed means that rain on Titan takes a long time to reach the surface from typical cloud altitudes. A drop falling from a cloud at 10 kilometers altitude at 2 meters per second would take nearly 90 minutes to reach the ground, compared to perhaps 20 minutes for a similar altitude cloud on Earth. During this long descent, the drop experiences varying conditions, passing through air of different temperatures, different methane vapor concentrations, and different wind speeds, all of which affect whether the drop grows through continued condensation, shrinks through evaporation, or maintains roughly constant size. The maximum size that methane drops can achieve before breaking apart is determined by the balance between surface tension, which holds the drop together, and aerodynamic forces, which tend to tear it apart. The lower surface tension of methane compared to water suggests smaller maximum drop sizes, but the slower terminal velocities on Titan reduce the aerodynamic forces, allowing larger drops to remain stable. Theoretical calculations suggest that methane drops on Titan might grow as large as 9 millimeters in diameter, substantially larger than typical rain on Earth, where drops exceeding 6 millimeters usually break apart into smaller droplets. When these large, slow-moving methane drops finally reach Titan's surface, they carry significant momentum despite their leisurely fall speed, because the density of liquid methane is about 0.42 times that of water, meaning a large methane drop has considerable mass. The impact of drops on the surface would create splashes, though the lower gravity means those splashes would develop in slow motion, with ejected droplets arcing high before falling back. Over time, steady rainfall would saturate the upper layers of Titan's porous, organic terrain, filling pores and crevices, eventually creating runoff that flows downslope towards streams and rivers. The erosive power of rain on Titan differs significantly from Earth. Each individual drop carries less energy because of the slower fall speed, suggesting that rain erosion might be less efficient. However, the larger drop sizes mean greater impact force per drop, and the duration of storms on Titan might be much longer than typical storms on Earth, with methane precipitation potentially continuing for days or even weeks once a storm system develops and taps into atmospheric methane reservoirs. Cassini observed the aftermath of rainstorms on several occasions with radar images showing darkening of surface terrain in regions where clouds had recently appeared, the darkening consistent with terrain wetted by rainfall. Some of these darkened regions persisted for weeks or months before fading, suggesting that liquid methane soaked into the surface or pooled in depressions took considerable time to evaporate in Titan's cold environment. Other darkened regions faded more quickly, perhaps because the rain fell on less porous terrain or because local conditions favoured rapid evaporation. The sound of methane rain falling on Titan would be unlike rain on Earth, distorted by the thick atmosphere's effect on sound propagation and by the different frequency spectrum of impacts from large, slow drops hitting the surface. The thick atmosphere damps high-frequency sounds while allowing low frequencies to propagate well, so methane rain might produce a deeper, more resonant sound than the familiar patter of terrestrial rain. Perhaps more of a gentle drumming than a patter. For anyone experiencing methane rain on Titan, the sensation would be peculiar. Large drops falling slowly enough to track with the eye, cool but not extremely cold because they're at ambient temperature, impacting gently because of the low fall speed, accumulating in puddles that might take hours or days to evaporate, flowing in rivulets that meander across the dark organic terrain, eventually feeding into streams that carry this alien rain toward distant lakes and seas. This is precipitation in slow motion, a delicate rain of natural gas falling through orange twilight, nourishing a landscape carved by liquid over millions of years. The first clear images of river channels on Titan came from the Huygens probe during its descent in 2005, showing dendritic drainage networks carved into the brighter terrain, resembling river systems on Earth when viewed from high altitude. These channels appeared dark in the images, suggesting they might be filled with liquid, or at least covered with fine-grained sediment transported by flowing methane. The similarity to terrestrial river networks was striking, providing visual evidence that despite the exotic chemistry, the basic physics of flowing liquid carving channels through erodible terrain operates the same way on Titan as on Earth. As Cassini's radar mapping progressed, these river systems emerged in greater detail, revealing networks that extend for hundreds of kilometers from highland source regions toward lowland lakes and seas, branching and merging in patterns that reflect the topography they flow through and the erosive power of liquid methane. The longest confirmed river system on Titan, named Vid Flumina, stretches more than 400 kilometers from elevated terrain near Titan's equator northward toward Kraken Mare, though whether it currently flows all the way to the sea or disappears into the terrain before reaching it remains uncertain. These rivers show characteristics familiar from terrestrial hydrology: meandering paths through lowlands, relatively straight courses through uplands, branching patterns that reflect drainage basin geometry, and what appear to be floodplains or valley floors wider than the active channel. The channels themselves vary in width from less than a kilometre to several kilometres for the largest systems, with depths that radar profiling suggests might range from a few metres to tens of metres, comparable to mid-sized rivers on Earth. The physics of river flow on Titan must account for methane's physical properties and Titan's environmental conditions. Liquid methane has a viscosity about 1/7 that of water, meaning it flows more easily, offering less resistance to flow for a given channel or geometry and slope. The lower viscosity suggests that for a given discharge rate and channel slope, methane rivers might flow faster than water rivers, though the lower gravity also affects the relationship between slope, velocity, and discharge in ways that partially compensate for the reduced viscosity. The slope of Titan's rivers appears quite gentle in most cases, with typical gradients of perhaps a few meters per kilometer, comparable to lowland rivers on Earth, like the Mississippi or the Amazon in their lower reaches. This gentle gradient reflects both Titan's modest topographic relief. The difference in elevation between highlands and lowlands generally amounts to only a few hundred meters across hundreds of kilometers, and the efficiency with which liquid methane can transport sediment even at slow flow velocities. That sediment consists not of silicate sand and clay like terrestrial rivers, but of organic particles, the accumulated debris of photochemistry in Titan's atmosphere, raining down over millions of years and accumulating in layers that can be eroded, transported, and deposited by flowing liquid. These organic sediments appear dark in radar images and optical photographs, giving Titan's lowlands their characteristic dusky appearance, and their small particle size and low density mean that even slow-moving methane rivers can carry them in suspension, creating flows that might resemble chocolate milk in appearance if we could see them clearly through the haze. The discharge of Titan's rivers varies seasonally and episodically, responding to precipitation patterns and evaporation rates. Most rivers probably flow only intermittently, running strongly after major rainstorms and dwindling to low flow or drying up entirely during dry periods. Some channels show bright radar-reflective interiors, suggesting they currently contain little or no liquid, while others appear dark and smooth, consistent with active flow or at least wet sediments. This variation suggests a hydrological system where some rivers flow perennially, fed by large drainage basins and perhaps by seepage of liquid from subsurface reservoirs, while others respond quickly to individual storm events. The transport of liquid from source to mouth can take considerable time on Titan. If a typical river flows at velocities comparable to walking speed, perhaps 1 to 2 meters per second, then liquid traveling the 400-kilometer length of Vidflumina would take more than 2 days, and likely much longer if the actual average velocity accounts for meandering and slower flow in wider sections. During this journey, the liquid methane carries its burden of organic sediment, abrading the water ice bedrock of the channel, creating deeper channels through millions of years of erosion. When these rivers finally reach lakes or seas, they often create features analogous to river deltas on Earth, spreading sediment into the quieter water of the lake, building up fan-shaped deposits that extend the land into the lake over time. Cassini's radar images show several clear examples of what appear to be deltaic features at the mouths of rivers feeding into Kraken, Mare, and other northern lakes. Bright radar returns suggesting coarser sediments in the delta region compared to the fine materials suspended in the lake itself. The erosive history of these river systems extends back millions, or perhaps billions of years, representing countless cycles of rainfall and runoff, evaporation and dry periods, erosion and deposition. The networks we see today reflect this long history, having carved their paths through trial and error as liquid methane sought the lowest route to the sea, creating channels that persist and deepen over geological time, gradually shaping Titan's landscape into a pattern that, despite the alien chemistry, looks hauntingly familiar to anyone who has studied terrestrial rivers from the air. If we could stand on a bridge over a Titan river in flood, we would see liquid methane flowing past at perhaps a walking pace, carrying dark organic sediment in suspension, making the normally clear liquid appear murky or opaque. The banks would consist of water ice, hard as rock at these temperatures, carved into shapes that reflect the river's varying discharge over its history. The sound would be the rush of liquid over obstacles, the splash against the banks, though distorted by the thick atmosphere into frequencies and timbres unfamiliar to human ears. And downstream, perhaps visible through the orange haze, the river would disappear into a lake or sea, delivering its cargo of methane and sediment to add to the accumulated hydrocarbons of Titan's largest liquid bodies. These are rivers that flow with what we would call gasoline, with natural gas condensed by cold into a liquid state. Rivers that carve stone made of ice, rivers that feed seas larger than the Great Lakes, rivers that remind us that water holds no monopoly on the processes of erosion and transport, that the physics of flowing liquid operates according to principles that transcend any particular substance. Understanding Titan's seasons requires first understanding Saturn's orbit around the Sun, an ellipse with a semi-major axis of about 1.4 billion kilometers that takes 29.5 Earth years to complete. This long orbital period means that each of Titan's seasons lasts more than 7 Earth years, creating climate patterns that unfold on timescales far longer than the annual cycle we experience on Earth. An individual human lifetime might encompass only 3 or 4 of Titan's years, barely enough to see the full cycle of its seasons repeat even once. Saturn's orbital eccentricity, the measure of how much its orbit deviates from a perfect circle, is approximately 0.057, meaning that Saturn's distance from the Sun varies from about 1.35 billion kilometers at perihelion. its closest approach to about 1.51 billion kilometers at aphelion, its farthest point. This variation affects how much solar energy Titan receives at different points in the orbit, with southern summer occurring near perihelion and northern summer near aphelion, creating an asymmetry in seasonal intensity that profoundly affects where liquid methane accumulates on Titan's surface. When Cassini arrived at Saturn in 2004, it was late southern summer on Titan, with the southern hemisphere tilted toward the sun and receiving maximum solar heating. The northern hemisphere, in winter, remained dark and cold at high latitudes, and radar mapping revealed that the northern polar region hosted hundreds of lakes, while the southern polar region showed only sparse liquid features. This distribution reflected the seasonal transport of methane from the warmer summer hemisphere, where evaporation exceeded precipitation, to the cooler winter hemisphere, where the opposite held true. As Saturn approached its August 2009 equinox, when the sun crossed Saturn's equatorial plane and day and night became equal in both hemispheres, Cassini observed dramatic changes in Titan's atmosphere and surface. Cloud activity increased near the equator, where it had been rare during the preceding years, and major storm systems appeared, including the massive September 2010 storm that covered 500,000 square kilometers. These equinoctial storms suggested that the transition between seasonal regimes creates atmospheric instability, perhaps through the interaction of circulation patterns that had been stable for years suddenly shifting as the thermal balance between hemispheres changed. Following the equinox, northern spring advanced into summer, and the northern hemisphere began receiving more solar energy than the south. Cloud activity shifted northward, appearing frequently over the northern lake district, and radar observations showed changes in surface features consistent with rainfall darkening terrain and possibly filling some of the smaller northern lakes that had appeared dry or partially dry during winter. Meanwhile, in the south, Ontario Lacus and other southern features showed evidence of shrinking, with shorelines receding as evaporation outpaced precipitation in the lengthening southern winter. The seasonal transport of methane represents a significant mass flux, with climate models suggesting that hundreds of kilometers cubed of liquid methane might evaporate from one hemisphere and be transported through the atmosphere to precipitate in the other over the course of a seasonal cycle. This transport affects not just the distribution of liquid on the surface, but also the atmospheric methane concentration, which varies with latitude and season in ways that Cassini's spectrometers mapped throughout the mission. The methane abundance in Titan's atmosphere, typically around 5% at the surface, shows enhancements at high latitudes during spring and summer, reaching 6 or even 7% in some locations, consistent with increased evaporation from warming lakes. At the same time, the opposite hemisphere shows slightly reduced methane concentrations as condensation removes methane vapor from the air. These variations drive atmospheric circulation, with air flowing from regions of high methane abundance toward regions of low abundance, creating wind patterns that Cassini tracked through cloud movements and that Huygens measured directly during its descent. The long-term stability of this seasonal cycle depends on a delicate balance between methane sources and sinks on Titan. Photochemistry in the upper atmosphere continuously destroys methane, breaking it down through reactions initiated by ultraviolet light from the sun, producing ethane, propane, and more complex hydrocarbons that rains onto the surface. Without replenishment, Titan's atmospheric methane should be depleted on timescales of tens of millions of years, geologically quite rapid. The persistence of methane in the atmosphere requires ongoing sources, perhaps outgassing from Titan's interior through cryovolcanism, perhaps release of methane trapped in water ice, clathrates below the surface, perhaps recycling of methane from the lakes and seas back into the atmosphere. The lakes themselves act as buffers in this cycle, storing large quantities of methane that can evaporate during summer and be replenished by precipitation during winter. The total volume of liquid hydrocarbons in Titan's lakes and seas has been estimated at roughly 7,000 cubic kilometers, with most residing in Kraken Mare and Ligeia Mare. This represents enough methane to supply Titan's atmospheric photochemistry for millions of years if the atmospheric inventory were destroyed and required complete replacement, though in reality the cycle operates more dynamically, with some methane being destroyed, while other methane evaporates from surface reservoirs. Observing the full seasonal cycle on Titan would require a mission spanning at least one Titan year, preferably 2 or 3, to see the patterns repeat and to distinguish seasonal variations from longer-term changes. Cassini's 13-year mission covered about half of one Titan year, from southern summer through equinox to early northern summer, providing our first direct observations of seasonal change on another world's methane cycle. The data revealed a system more complex and dynamic than pre-mission models had suggested, with regional variations, episodic events, and feedback loops between atmosphere and surface creating weather and climate patterns that continue to challenge our understanding. As we imagine standing on Titan through a complete seasonal cycle, we see the landscape transformed slowly over years. The warming of northern lakes, the evaporation of southern pools, the shift in cloud patterns from south to north, the gradual changes in river flow and rainfall distribution, all proceeding at a pace that makes even the patient observations of a spacecraft seem rushed. This is weather and climate at the pace of human careers rather than human vacations. A reminder that Earth's rapid seasonal cycle is unusual, that most worlds in the outer solar system experience change on timescales that require decades of observation to fully understand. Among the many discoveries made by Cassini during its exploration of Titan, few proved as puzzling and intriguing as the transient bright features that appeared and disappeared in radar images of the northern seas, particularly Ligeia Mare. These features, dubbed Magic Islands by the science team, showed up as bright radar returns in some passes and disappeared in subsequent observations of the same location, suggesting temporary phenomena rather than permanent islands or seafloor topography. The first clear detection came in July 2013, when radar images of Ligeia Mare revealed a bright feature covering about 75 square kilometers near the southwestern shore, in a region that had appeared dark and featureless in earlier observations. Subsequent monitoring of this feature showed it evolving over time, changing in brightness and extent, sometimes appearing to fragment into multiple smaller bright regions, sometimes coalescing back into a single feature, and eventually fading below the detection threshold, only to reappear in later observations. This behavior ruled out simple explanations, like permanent islands, that happened to be missed in earlier imaging. Instead, it pointed to something dynamic, something appearing and disappearing, or at least changing its radar properties on timescales of weeks to months. Several hypotheses emerged to explain these magic islands, each drawing on different aspects of Titan's unique environment and the physics of liquid methane seas. One early suggestion proposed that the bright features might represent waves or roughened surface conditions, with wind driving the liquid into white cap-like structures that create strong radar returns. On Earth, roughened water surfaces appear bright in radar images, while calm water appears dark, a principle used in maritime radar to detect wave patterns. However, the longevity of Titan's magic islands, persisting for months rather than hours, argued against simple, wind-driven waves unless Titan's seas support standing wave patterns or resonances that persist much longer than would be expected. A second hypothesis suggested that the bright features might represent floating masses of solid material, perhaps organic solids produced through photochemistry and precipitating from the atmosphere onto the lake's surface, or perhaps solids coming out of solution from the liquid itself analogous to sea ice forming in Earth's polar oceans, but consisting of frozen hydrocarbons rather than frozen water. The buoyancy of such solids would depend on their density relative to the liquid methane-ethane mixture, and calculations showed that many plausible organic compounds could indeed float, creating temporary islands that would slowly dissolve or sink as conditions changed. A third explanation focused on bubbles of nitrogen gas rising from the lake depths, forming fields of bubbles or foam at the surface that would create bright radar returns. This hypothesis drew on the fact that nitrogen dissolves in liquid methane and ethane, with solubility depending on temperature and pressure. In the deeper parts of Ligeia Mare, where pressure is higher and temperature might be slightly lower, nitrogen could be stored in solution at concentrations exceeding what would be stable at the surface. If some disturbance, seasonal warming, a submarine landslide, or simply the slow overturning of the lake, brought this nitrogen-saturated liquid toward the surface, the reduced pressure would cause nitrogen to come out of solution rapidly, creating fizzing or effervescence analogous to opening a carbonated beverage. Each of these hypotheses found some support in the observations, and none could be definitively ruled out with the available data. The transient nature of the features seemed most consistent with bubbles or suspended particles rather than solid floating masses, which should be more stable over time. The locations of the magic islands, often appearing in the same general regions of Ligeia Mare, even if not precisely the same spots, suggested that certain areas of the sea might be more prone to whatever process creates these features, perhaps due to local wind patterns, bathymetry, or composition. Laboratory experiments on Earth attempted to recreate conditions that might produce magic island-like phenomena in liquid methane-ethane mixtures. These experiments explored how nitrogen comes out of solution under temperature and pressure changes, how organic solids might precipitate and float in hydrocarbon liquids, and how waves form on low-viscosity liquids in low-gravity, high-pressure conditions. The results provided insights, but could not perfectly replicate Titan's conditions, leaving significant uncertainty about which mechanism, if any single one, explains the observations. The brightness and persistence of the magic islands also varied, with some appearing as very bright features that stood out dramatically from the dark lake surface, while others showed up as only subtle brightness variations, barely distinguishable from radar noise. This variability suggested that the phenomenon might occur at different scales or intensities, with some events producing large, obvious features, while others created smaller or more diffuse effects. Tracking the evolution of individual features proved challenging because Cassini's radar could only image any given location during specific flybys, meaning gaps of weeks or months between observations of the same spot, too infrequent to capture rapid changes, but frequent enough to show that substantial evolution occurred between passes. Toward the end of Cassini's mission, as northern summer progressed and solar heating warmed Ligeia Mare, scientists hoped to observe increased magic island activity, potentially driven by seasonal warming, destabilizing dissolved nitrogen, or promoting convection that might bring supersaturated liquid from depth to the surface. Some evidence suggested a possible increase in transient features, though the limited remaining opportunities for radar imaging made it difficult to establish definitive trends. The final images of Ligeia Mare, returned by Cassini in April 2017, showed several bright features that might have been magic islands, leaving the mystery partially unresolved for future missions to investigate. These magic islands represent one of the frontiers of our understanding of Titan, a phenomenon we can observe but not yet fully explain, a reminder that even after 13 years of dedicated exploration, this world retains mysteries that challenge our ability to interpret remote sensing data and to understand processes occurring in environments we cannot directly sample. Whether they are waves or bubbles, floating solids or suspended sediments, fields of nitrogen foam or something entirely unexpected, the magic islands of Ligeia Mare stand as Saturn's testimony to Titan's dynamic nature, to the ongoing processes that make it not just a frozen relic, but an active, changing world. Let us, for a moment, leave behind the orbital perspective of spacecraft and radar maps, and instead imagine ourselves standing on Titan's surface, suited and protected against the cold and the alien atmosphere, looking out across one of the northern lakes as northern summer reaches its peak. What would we actually experience on this most distant shore humanity has yet discovered? What would our senses report filtered through the technology that would keep us alive on a world so fundamentally hostile to human biology? The first sensation would be the light, or rather, the lack of it. Even at noon on a cloudless day, Titan's surface receives only about 1/1000th the illumination that Earth's surface receives under similar conditions. The sun, diminished by distance to a bright star rather than the blazing disk we know, provides barely enough light for human eyes adapted to darkness to see the landscape. Everything exists in perpetual twilight and orange-brown dimness comparable to the light about 15 minutes after sunset on Earth, or perhaps the interior of a building lit by dim incandescent bulbs. Through amber glass, that orange colour permeates everything, the result of the thick organic haze layers that scatter and absorb sunlight passing through Titan's atmosphere. The haze particles, complex organic molecules called tholins, preferentially scatter blue and green light while allowing orange and red wavelengths to penetrate, creating the characteristic colour that gives Titan its appearance from space. This orange illumination makes judging distances difficult, flattens shadows, and gives the landscape a surreal dreamlike quality that would require time to adjust to. Looking upward, the sky fades from darker orange-brown near the horizon to lighter orange overhead, where the thinnest part of the atmosphere intervenes between observer and space. On rare occasions when the haze clears or thins, Saturn might be visible during part of Titan's 16-day orbit around the gas giant, appearing as a pale disk, perhaps showing bands and rings, though likely muted by atmospheric scattering. More often, the sky presents only diffuse orange glow, featureless except perhaps for brighter regions marking the sun's position. The air around us, though we could not breathe it, pushes against our suit with pressure about 50% greater than Earth's sea level atmosphere, a difference we might notice in the stiffness of suit joints and the resistance to movement. But this same thick atmosphere provides excellent protection against micrometeorites and cosmic radiation, serving as a shield that spacecraft in airless environments cannot enjoy. The temperature reads -179 degrees Celsius on our suit instruments, but the thick atmosphere conducts heat away from the suit more efficiently than thin or no atmosphere would, making thermal management a critical engineering challenge. The gravity tugs at us with only about 1/7 Earth's pull, transforming movement into something between walking and floating. Each step could cover several meters in bounding strides, and jumping would launch us several times higher than on Earth, though the thick atmosphere creates air resistance that damps rapid motion more than in Earth's thinner air. Dropping a rock would see it fall in slow motion, accelerating gradually. Taking seconds to cover distances it would traverse in a fraction of a second on Earth. Turning our attention to the lake before us, we see a surface that appears mirror smooth in the still air, reflecting the orange sky in perfect detail, extending to a horizon that seems closer than on Earth because Titan's smaller radius curves the surface away more sharply. The liquid itself looks clear, at least near the shore, where depth allows light to penetrate and reflect from the bottom, though deeper water appears darker, perhaps black, its transparency allowing our gaze to penetrate meters downward before losing detail in the depths. The shore beneath our feet consists of rounded pebbles and cobbles of water ice, mechanically worn by wave action into smooth shapes, interspersed with patches of dark organic sediment, fine-grained material that might be sticky or loose depending on moisture content. Picking up an ice pebble would reveal it as surprisingly hard, essentially rock-like at these temperatures, though our suit gloves would prevent direct tactile sensation. Throwing this pebble into the lake would produce a slow-motion splash, with droplets arcing upward and outward in the low gravity, before falling back, ripples spreading outward more slowly than on water because of methane's lower surface tension. The sound landscape on Titan would be unlike anything experienced on Earth. The thick atmosphere carries sound well, perhaps better than Earth's atmosphere in some frequency ranges, but the cold temperature increases sound velocity and shifts the frequencies at which resonances occur. Our voice, transmitted through the atmosphere to a companion suit radio, might sound strange, distorted by the medium's properties. The sound of methane lapping at the shore, if any waves exist, might resonate at lower frequencies than water waves, creating a deeper, more ominous sound than the familiar ocean surf. Looking along the shoreline, we might see river mouths where darker channels meet the lake, perhaps actively flowing with liquid methane, or perhaps dry until the next storm. We might observe terraces marking former lake levels, bright deposits of material left behind when the liquid stood higher, testament to the seasonal variations that move methane from one reservoir to another as years pass. We might see organic sediment deposited in deltas, building land into the lake, or notice the absence of the biological debris, driftwood, seaweed, shells that characterizes every Earth shore. The silence would be profound, broken only by the sounds we make ourselves and perhaps by the whisper of wind through the thick atmosphere. No birds, no insects, no rustle of vegetation, no sound of other animals, because Titan appears lifeless, a world of chemistry without biology, of organic molecules without organization into living systems. This absence, this silence of life, would perhaps impress itself most deeply on our consciousness, reminding us that Earth's vibrant cacophony of biological activity represents a rare state, that most worlds, even with complex chemistry, remain silent and still. As we stand on this shore, looking across this alien lake, beneath this alien sky, we might feel both the strangeness and the familiarity of this place, recognizing processes we understand playing out with substances we know only from industrial applications on Earth, creating landscapes that echo our home while remaining utterly foreign in detail. This is Titan at human scale, not as pixels in a radar image or numbers in atmospheric models, but as a place we might someday visit, experiencing directly what we now know only through instruments and imagination. Titan's atmosphere functions as a vast natural laboratory for organic chemistry, processing simple starting materials through complex reaction. Pathways that produce thousands of different molecules, many of which fall to the surface and accumulate over geological timescales. Understanding this atmospheric chemistry helps explain not only Titan's present state, but also provides insights into the kind of chemistry that might have occurred on early Earth before life emerged, making Titan a natural experiment in prebiotic chemistry unfolding on a planetary scale. The chemistry begins in Titan's upper atmosphere, where ultraviolet light from the sun, though greatly reduced by distance, still carries enough energy to break molecular bonds in methane and nitrogen. When a UV photon strikes a methane molecule, it can dissociate the molecule into a methyl radical, CH3, and a hydrogen atom, both of which are highly reactive species that readily participate in subsequent reactions. Similarly, nitrogen molecules can be dissociated, creating nitrogen atoms that can react with hydrocarbon fragments to form nitriles, compounds containing carbon-nitrogen bonds. These initial reactions set off a cascade of further chemistry, with radicals combining to form ethane, propane, butane, and longer-chain hydrocarbons, while nitrogen atoms insert into these molecules, creating compounds like hydrogen cyanide, HCN, cyanoacetylene, HC3N, and more complex nitriles. The products of these reactions continue reacting, building up larger and more complex molecules through processes that include polymerization, where small molecules link together to form chains or networks, creating the organic haze particles that give Titan its characteristic orange color. These haze particles, collectively called tholins from a Greek word meaning muddy or unclear, consist of complex mixtures of hydrocarbons and nitriles with molecular weights ranging from hundreds to thousands of atomic mass units, far larger than the simple methane and nitrogen molecules they formed from. Laboratory simulations of Titan's atmospheric chemistry, where mixtures of methane and nitrogen are exposed to UV light or electrical discharges, produce material strikingly similar to what spectroscopy observes in Titan's haze, confirming that we understand at least the broad outlines of the chemical processes occurring. The tholins rain down onto Titan's surface as small particles, perhaps a few micrometers in diameter, accumulating over millions of years to form the dark organic layer that covers much of Titan's lowlands. This layer might be meters or tens of meters thick, representing billions of years of atmospheric chemistry, a reservoir of organic material that dwarfs any comparable accumulation on Earth, where biological processes consume organic molecules and where oxidation in the presence of free oxygen destroys most organic material exposed at the surface. Some of the more volatile products of atmospheric chemistry, compounds like ethane, propane, and benzene, dissolve in the methane rain as it falls through the atmosphere, getting carried to the surface in solution and potentially accumulating in the lakes and seas. This process might explain why Titan's lakes contain substantial dissolved ethane, despite ethane being produced in the atmosphere rather than evaporating from surface sources. The lakes thus act as collection points, not just for methane, but for the full range of organic molecules soluble in liquid hydrocarbons. The diversity of molecules detected in Titan's atmosphere and predicted by models is staggering. Cassini's instruments identified dozens of distinct compounds, including polycyclic aromatic hydrocarbons, PAHs, related to molecules like naphthalene and anthracene, complex nitriles, carbon dioxide, water vapor, and numerous others. Each of these species tells part of the story of how simple starting materials elaborate into chemical complexity through energy inputs from sunlight and perhaps from charged particles in Saturn's magnetosphere interacting with the upper atmosphere. One particularly intriguing aspect of Titan's chemistry involves the formation of amino acids and nucleotide bases, the building blocks of proteins and nucleic acids in terrestrial biology. Laboratory simulations have shown that when tholins produced in Titan-like conditions are exposed to liquid water, they can form amino acids, suggesting that if liquid water ever appeared on Titan's surface, perhaps through meteorite impacts melting ice, or through cryovolcanic activity, some of the organic material accumulated over geological time might elaborate into molecules directly relevant to life as we know it. This connection between Titan's chemistry and prebiotic chemistry on early Earth makes Titan valuable as an analogue, a place where we can study processes that might have operated on our own planet 4 billion years ago, before the origin of life, when Earth's atmosphere likely contained little free oxygen, and when organic molecules accumulated through atmospheric chemistry, similar to what we observe on Titan. The difference is matter, of course. Earth's early atmosphere probably contained more carbon dioxide and water vapor than Titan's, and Earth's surface was much warmer. but the basic principle of building complex organic molecules from simple atmospheric gases through photochemistry appears universal. The energy available to drive Titan's atmospheric chemistry comes primarily from solar UV radiation, but also from cosmic rays and from charged particles in Saturn's magnetosphere, which create ionization in the upper atmosphere that initiates some chemical reactions. The total energy input is modest compared to Earth, perhaps 100 times less UV flux because of the greater distance from the Sun, but this energy input has operated for billions of years, steadily processing methane and nitrogen into more complex forms. The long-term evolution of Titan's atmospheric chemistry depends critically on the source of methane, which is continuously destroyed but must be replenished to maintain the observed atmospheric concentration. Without replenishment, calculations suggest Titan's atmospheric methane should be depleted in tens of millions of years, too short a time for Saturn's 4.5 billion year history. The source might be outgassing from the interior, perhaps through cryovolcanism that releases methane trapped in water ice clathrates, or it might represent recycling of methane from surface reservoirs, or some combination of processes that maintains a rough equilibrium between destruction and replenishment. As we consider Titan's role as an organic chemistry laboratory, we marvel at the complexity that emerges from simple starting conditions, at the way energy flowing through a system can organize matter into structures far from thermodynamic equilibrium, creating diversity and complexity that, while not living, shares some characteristics with the chemical systems that support life. This is chemistry for its own sake, unguided by biology, proceeding according to thermodynamics and kinetics alone, yet producing molecules that in different circumstances might serve as the foundation for life's emergence. The question of whether life could exist in Titan's methane lakes strikes at the heart of our understanding of what life requires, challenging assumptions based on the only example we know: carbon-based, water-dependent life on Earth. Every organism we have ever studied, from bacteria to blue whales, relies on liquid water as its solvent, the medium in which biochemical reactions occur, in which molecules dissolve and diffuse, in which the complex molecular machinery of cells operates. Water's unique properties, its polarity, its capacity to form hydrogen bonds, its ability to dissolve both ionic and some organic compounds, make it extraordinarily well suited for life as we know it. But does life require water, or merely a liquid solvent with appropriate properties? Titan's lakes offer liquid methane and ethane as potential solvents for hypothetical life, and these substances differ profoundly from water in ways that would require fundamental reimagining of biochemistry. Methane is nonpolar, meaning it does not form hydrogen bonds and does not dissolve ionic compounds like salts. This property makes it an excellent solvent for other nonpolar organic molecules, which is why it dissolves the various hydrocarbons and larger organic molecules present on Titan. But it means that the kind of biochemistry we see on Earth, with charged amino acids, phosphate groups, and ionic interactions stabilizing protein structures, simply would not work in liquid methane. Any life based on methane as a solvent would need to employ completely different molecular strategies. In 2015, a team, researchers at Cornell University, led by chemical engineering professor Paulette Clancy, published theoretical work suggesting what they called azotosomes, hypothetical cell membranes that could remain stable in liquid methane at Titan's temperatures. These azotosomes would be composed of small organic nitrogen compounds like acrylonitrile, forming structures analogous to the phospholipid bilayers that form cell membranes in water-based life, but stable in the very different chemical environment of liquid methane. The energy sources available to power methane-based life on Titan present another challenge. On Earth, the ultimate energy source for almost all life is sunlight captured through photosynthesis, or chemical energy from redox reactions, particularly reactions involving oxygen, either as an oxidant or as a product of photosynthesis. Titan's surface receives very little sunlight, and oxygen is essentially absent, locked up in water ice and carbon monoxide rather than existing as free O2. However, Cassini's instruments detected the presence of hydrogen gas in Titan's atmosphere being consumed near the surface, and the presence of acetylene and other reactive hydrocarbons on the surface, suggesting potential chemical energy sources. A 2005 paper by astrobiologist Chris Mckay and planetary scientist Heather Smith proposed that methane-based life on Titan might metabolize hydrogen and acetylene, combining them in reactions that release energy, with the waste products being methane and energy that the organism could use to drive its own chemistry forward. This metabolism would be analogous to respiration on Earth, where oxygen oxidizes organic molecules and releases energy, but adapted to Titan's chemistry. The challenge is that such reactions proceed very slowly at Titan's cold temperatures, and it is unclear whether they could release energy quickly enough to support active metabolism. The temperature itself presents perhaps the greatest obstacle to life on Titan. At -179 degrees Celsius, molecular motion is greatly reduced compared to Earth's surface temperatures. Chemical reactions that occur rapidly in warm water might take millions of years in liquid methane at Titan's temperature, making metabolism, as we understand it, essentially impossible without invoking exotic biochemistry far beyond what we currently imagine. Enzymes, the biological catalysts that speed up reactions in terrestrial life, work by lowering activation energies and providing favorable geometries for reactions. But the degree of speed up required to make Titan's chemistry support lifelike processes would need to be extraordinary. Despite these challenges, the possibility cannot be dismissed entirely. Life on Earth exists in extraordinary diversity, exploiting environments from deep ocean hydrothermal vents to solid rock kilometers underground, from acidic hot springs to Antarctic ice. Each extreme environment requires specialized adaptations, different molecular strategies for surviving and reproducing, yet all share the fundamental framework of water-based biochemistry. Perhaps methane-based life would represent simply another extension of life's adaptability, using different solvents and different chemistry, but operating according to the same basic principles of harnessing energy flows to maintain organization far from thermodynamic equilibrium. Some scientists have suggested looking for anomalous consumption of atmospheric hydrogen or surface acetylene as potential biosignatures, signs of metabolic activity that might indicate life consuming these chemicals for energy. Cassini's final passes through Titan's atmosphere did detect vertical transport of hydrogen that might reflect surface consumption, though abiotic processes could also explain this observation. Similarly, the apparent absence or lower than expected concentration of acetylene on Titan's surface might reflect biological consumption, or might simply indicate that acetylene gets incorporated into other molecules through non-biological chemistry. The search for life in liquid methane represents a frontier where astrobiology meets speculative biochemistry, where we must question our assumptions about what life requires and expand our conception of habitability. If life can exist in liquid methane at temperatures nearly 200 degrees below water's freezing point, then the number of potentially habitable worlds in the universe expands dramatically, including not just planets in their star's habitable zone, where liquid water can exist, but also the many moons of gas giants throughout every planetary system, where organic chemistry and liquid solvents might enable biology. The implications extend beyond Titan to other worlds in our solar system and beyond. Jupiter's moon Europa and Saturn's moon Enceladus likely harbour subsurface oceans of liquid water, making them prime targets in the search for water-based life. But if methane can support life, then numerous other moons and even some regions of planets might qualify as habitable, each requiring different biochemical solutions to the challenges of energy extraction, molecular organization, and reproduction. The cosmos becomes not less alien, but more pregnant with possibility, with potential for life in forms we can barely imagine. Yet we must remain humble about our ignorance. The only life we know is the life on Earth, a single example that, for all its diversity, represents a single origin event, a single solution to the problem of how to organize matter into self-sustaining, reproducing systems. We cannot be certain that our solutions are the only ones, nor can we be certain that vastly different solutions are possible. Until we discover a second origin of life, whether on Titan or Europa, on Mars or Enceladus, or somewhere in the vast universe beyond our solar system, we cannot definitively answer whether life requires water or merely requires a suitable solvent and energy source. For now, Titan stands as a test case, a place where we can look for signs of exotic biochemistry, where future missions can search for metabolic processes, where we might discover that life's creativity exceeds even our expanded imagination. And if Titan proves lifeless, as many scientists suspect it is, that negative result also teaches us something valuable: that life, despite its tenacity on Earth, faces limits in how far it can adapt to alien conditions, that some environments, however rich in organic chemistry, remain merely chemical systems without crossing the threshold into biology. As you drift towards sleep tonight, ponder this question. In the universe of possibilities, does life represent a narrow path threading through specific requirements, or a broad highway with many lanes leading toward complexity and organization? Titan, with its lakes of liquid methane beneath an orange sky, may someday help us answer. The success of the Cassini-Huygens mission in revealing Titan's methane lakes and complex chemistry has inspired plans for future missions that would explore this world in even greater detail, moving beyond orbital reconnaissance and single probe landing to sustained surface presence, aerial exploration, and perhaps even sailing on Titan's seas. These future missions, some approved and in development, others still in the proposal stage, promise to answer questions that Cassini could only raise and to provide the kind of detailed, long-duration exploration that transforms our understanding of a world. The most advanced of these future missions is Dragonfly, a nuclear-powered rotorcraft developed by the Johns Hopkins Applied Physics Laboratory and selected by NASA in 2019 as part of the New Frontiers program. Scheduled for launch in 2028, with arrival at Titan in 2034, Dragonfly will explore Titan's surface by flying between sites of scientific interest, covering potentially hundreds of kilometers during its primary mission. The concept takes advantage of Titan's thick atmosphere and low gravity, which make flight easier than on Earth or Mars, allowing a vehicle roughly the size of a small car to fly using rotors similar to those on large terrestrial drones. Dragonfly's nuclear power source, a multi-mission radioisotope thermoelectric generator, MRTG, similar to those powering the Curiosity and Perseverance Mars rovers, provides the advantage of operating regardless of sunlight availability, crucial on a world where solar energy is minimal and where nights last more than 7 Earth days. The power enables not just flight, but also extensive scientific instrumentation, including a mass spectrometer capable of analyzing the detailed chemistry of Titan's surface materials, a drill to obtain samples from beneath the surface layer, cameras to image the landscape and inform flight planning, and atmospheric sensors to characterize weather conditions. The mission plan calls for Dragonfly to land initially near Titan's equator, in the region explored by Huygens, then gradually work its way towards Selk Crater, a 90-kilometer diameter impact structure where the energy of impact likely melted water ice and created a temporary lake of liquid water that might have persisted for hundreds or thousands of years. The organic materials present on Titan's surface would have mixed with this liquid water, potentially driving prebiotic chemistry similar to what occurred on early Earth. By sampling materials around and potentially within Celt Crater, Dragonfly may find evidence of chemical processes that bridge the gap between non-living chemistry and the reactions that could lead toward life. Beyond Dragonfly, planetary scientists have proposed even more ambitious missions, including landers designed specifically to operate at the shores of the northern seas, submarines that could dive beneath the surface of Kraken Mare or Ligeia Mare to explore their depths, and sample return missions that would bring Titan material back to Earth for detailed laboratory analysis. Each of these concepts faces substantial technical challenges, but each offers scientific rewards that justify the engineering investment required to overcome those challenges. A Lakelander mission would address questions about lake composition, depth and dynamics that radar observations from orbit cannot fully resolve. Such a lander might include a floating platform capable of measuring waves, currents, and tides, instruments to sample the liquid and analyze its chemistry in detail, cameras to observe the shoreline and any changes over time, and perhaps a tethered probe that could be lowered into the lake to measure depth and composition at different levels. The challenge lies in designing systems that can operate in liquid methane at extreme cold, with materials and lubricants that remain functional at temperatures that would freeze most substances solid. The submarine concept pushes engineering even further, requiring a vehicle that can withstand the pressure of Titan's lakes, navigate in complete darkness beneath the surface, collect samples of liquid and lake floor sediment, and transmit data back to an orbiter or lander serving as a relay. The scientific payoff would be unprecedented. Direct measurement of lake depth, mapping of lake floor topography, discovery of whether anything like hydrothermal vents exists, releasing heat and chemicals from Titan's interior into the liquid above, an observation of any processes occurring in the liquid column that might hint at exotic chemistry or even biology. A Titan sample return mission would require solving multiple formidable challenges, landing on the surface, collecting representative samples of both solid organics and liquid from a lake, launching those samples into Titan orbit, rendezvousing with an orbiter, and then returning to Earth across more than 1 billion kilometers of space. The technological hurdles are comparable to those of a Mars sample return, itself one of the most complex missions ever conceived, but the scientific value of having Titan material available for analysis in terrestrial laboratories, using instruments far more sophisticated than can be sent to Titan, would revolutionize our understanding of organic chemistry in the outer solar system. International collaboration could enable missions beyond what any single space agency could accomplish. A Titan exploration program involving NASA, the European Space Agency, the Japan Aerospace Exploration Agency, and other partners could deploy multiple spacecraft working together. An orbiter for communications relay and continued global monitoring, an aerial vehicle like Dragonfly for mobility and regional exploration, a Lakelander for detailed study of Titan's seas, perhaps even the submarine or sample return elements. Such collaboration would parallel the successful model of Cassini-Huygens while extending it to an entire campaign of Titan exploration spanning decades. The timeline for these future missions extends into the 2030s and 2040s, with Dragonfly arriving in 2034, and any subsequent missions requiring many more years of development, travel time, and operation. For those of us alive today, Titan exploration will unfold over the course of our lifetimes, each new mission building on the discoveries of the previous, gradually transforming this alien moon from a mysterious orange sphere into a world we understand in intimate detail, with maps of its lakes and rivers, catalogues of its organic chemistry, understanding of its weather and seasons, and perhaps answers to the profound question of whether life can exist in environments radically different from Earth. The technical challenges of exploring Titan should not be underestimated, but neither should the human capacity for innovation when confronted with compelling scientific questions. The engineers who will design future Titan missions are perhaps in school today, learning the physics and chemistry, the systems engineering and project management that will enable them to send robots to sail on alien seas, to fly through orange skies, to drill into organic sediments accumulated over billions of years, to search for evidence of chemistry and perhaps biology unlike anything on Earth. As we imagine these future missions, we can picture the data they will return. High-resolution images of Titan's lakes captured by dragonfly, flying low over their surfaces. Chemical analyses revealing the exact composition of different lakes and how they vary with season and location. Measurements of lake depth creating three-dimensional maps of the lake floors, observations of weather systems and storm evolution that transform our theoretical understanding into empirical knowledge. Each discovery will raise new questions, inspire new missions, draw humanity deeper into engagement with this most remarkable of worlds. The exploration of Titan represents one of the great adventures awaiting humanity, a journey into an alien chemistry so different from our everyday experience, yet governed by the same physical laws, operating under conditions that challenge our engineering but not our capacity to understand. And in pursuing this exploration, in sending our mechanical envoys across the solar system to swim in seas of methane, we extend the ancient human drive to explore beyond the horizon, to discover what lies in unmapped territories, to transform the unknown into the known. As we reach the end of our journey through Titan's methane lakes and orange skies, through its organic chemistry and alien landscapes, we return to the question of what this strange moon tells us about our own world, about the Earth that spawned us, and the processes that made life possible on our blue planet. Titan serves as more than an object of curiosity. It functions as an analogue, a mirror reflecting aspects of Earth's history and potentially its future, a place where we can study processes that once shaped our world or might someday transform it again. The most direct parallel lies between Titan's atmosphere and chemistry today, and Earth's atmosphere and chemistry before the origin of life, roughly 4 billion years ago. Early Earth likely possessed an atmosphere rich in nitrogen but lacking free oxygen, with methane, carbon dioxide, and other gases present in varying amounts depending on volcanic outgassing and photochemical processes. Organic molecules would have formed through atmospheric chemistry driven by solar ultraviolet radiation and lightning, raining down onto the surface where they could accumulate in bodies of water, creating the primordial soup from which, through mechanisms still not fully understood, life eventually emerged. Titan provides a natural laboratory where similar chemistry unfolds today, where we can observe the products of atmospheric photochemistry accumulating over geological time, where organic molecules exist in abundance without being consumed by biological processes or destroyed by oxidation in an oxygen-rich atmosphere. By studying Titan's chemistry, we learn what kinds of molecules form spontaneously from simple starting materials, what reaction pathways are most productive, what environmental conditions favor complexity and diversity in organic chemistry. This knowledge informs our understanding of the prebiotic chemistry that preceded life on Earth and helps us develop realistic scenarios for how the building blocks of life might have accumulated. The differences between Titan and early Earth matter as much as the similarities. Earth was much warmer even before life emerged, with surface temperatures that allowed liquid water to exist in abundance. This warmth meant faster reaction rates, more dynamic chemistry, and the possibility for reactions that cannot occur at Titan's frigid temperatures. Earth likely had more carbon dioxide in its early atmosphere, providing carbon for organic synthesis, and volcanic activity delivered a range of chemical elements to the surface and atmosphere. Earth's larger size and stronger gravity prevented light molecules like hydrogen from escaping as easily as they do from Titan, affecting the overall chemical inventory. Yet despite these differences, Titan and early Earth share enough commonality to make Titan relevant as an analogue. Both possess thick nitrogen atmospheres. Both experience photochemistry that builds complex molecules from simple starting materials. Both have mechanisms for concentrating organic molecules, whether in Titan's lakes and surface sediments, or in Earth's early oceans and tidal pools. Both operate at temperatures where chemistry can proceed, though at very different rates. By comparing the two, we learn what is universal about prebiotic chemistry and what is specific to particular environmental conditions. Looking forward rather than backward, Titan might also offer insights into Earth's distant future, billions of years from now, when the Sun exhausts its hydrogen fuel and begins its transformation into a red giant. During this phase, the Sun will expand dramatically, becoming perhaps 200 times its current diameter, engulfing Mercury and Venus, and possibly even Earth. But long before the Sun physically swallows our planet, the increasing solar luminosity will make Earth uninhabitable, evaporating the oceans, stripping away the atmosphere, transforming our living world into a desiccated ruin. As Earth dies, the outer solar system might briefly flourish. The increased solar energy reaching Saturn's distance will warm Titan substantially, perhaps raising its surface temperature high enough to melt some of the water ice that currently forms its bedrock. Liquid water could appear on Titan's surface, interacting with the vast accumulations of organic material, potentially driving chemistry that could not occur at current temperatures. Whether this warming could last long enough for life to emerge remains doubtful. The red giant phase persists for only hundreds of millions of years, perhaps not enough time for the slow process of abiogenesis, but Titan might experience a brief period of enhanced chemical activity before the Sun finally exhausts its fuel and collapses into a white dwarf, leaving the solar system frozen and dark. This vision of Titan's future and Earth's doom reminds us that planets and moons do not remain static, but evolve over billions of years through processes driven by their star's evolution, by internal heat engines, by impacts and volcanism and atmospheric change. Titan today represents just one moment in its long history, with a past we can only infer and a future we can only imagine. The methane we see being destroyed by photochemistry today must have been more abundant in Titan's past, or must be continuously replenished. Otherwise it would have been depleted long ago. The organic material accumulating on the surface today will continue accumulating until some future event, perhaps the Sun's evolution, perhaps something else, transforms Titan's environment again. On a more immediate timescale, Titan teaches us about climate systems and how atmospheres respond to changing conditions. The seasonal transport of methane from one hemisphere to the other, the formation of clouds and precipitation, the interaction between surface liquid and atmospheric vapor, all parallel processes that occur on Earth with water. By studying Titan's climate, we improve our understanding of climate dynamics in general, learning principles that apply not just to alien worlds, but to our own planet's response to changing greenhouse gas concentrations, to shifting ice coverage, to the complex feedbacks between atmosphere, ocean, and land. The ethical and philosophical implications of Titan also deserve reflection. If we discover that life can exist in liquid methane, or if we find evidence that prebiotic chemistry on Titan has progressed further toward complexity than we currently recognize, how does that change our responsibility toward this world? Do we have an obligation to preserve Titan in its natural state, uncontaminated by Earth life, even if we could terraform it or extract resources from it? These questions, which might seem abstract now, become concrete as our capability to affect other worlds increases, as missions like Dragonfly begin exploring the surface and potentially disturbing the very chemistry they seek to study. As our exploration of Titan continues, as Dragonfly flies through those orange skies in the 2030s, as future missions perhaps sail on Kraken Mare or dive into Ligeia's depths. We will learn more about this world's mysteries, the source of its methane, the nature of its magic islands, the full inventory of its organic chemistry, the history recorded in its sediments, perhaps even whether any form of life or proto-life exists in its lakes or beneath its surface. Each discovery will add detail to our understanding, filling in the picture that Cassini began sketching, transforming Titan from a mysterious orange orb into a fully realized world with its own character and story. But beyond the scientific discoveries, beyond the technical achievements of robotic exploration, beyond even the question of life in methane lakes, Titan offers something more profound: perspective on Earth's place in the cosmos and our own existence as conscious beings capable of exploring worlds we can never directly experience. When we contemplate Titan, when we imagine standing on those methane shores beneath that orange sky, when we marvel at chemistry so alien yet governed by familiar physical laws, we step outside our everyday experience and encounter the universe on its own terms, vast and strange and beautiful. The lakes are calm tonight on Titan's northern shore. Methane laps gently at the water ice beach, moved by winds we cannot feel, creating ripples that spread and interfere and eventually dissipate into stillness. The orange sky glows with its perpetual twilight, illuminated by sun too distant to warm, too dim to banish the cold. Saturn rises slowly over the horizon when orbital geometry permits, rings edge on or tilted, bands of clouds sliding past in slow rotation. And beneath it all, chemistry unfolds, molecules react, complexity emerges from simplicity, all without witness except our distant spacecraft, and now, through their data, our minds reaching across 1 billion kilometers to understand and appreciate and wonder. Thank you for joining us here on Whispering Universes for this exploration of Titan's methane lakes, of Saturn's largest moon at twilight, of chemistry in cold and dark places, creating landscapes that challenge and inspire. As you drift towards sleep, let yourself imagine that alien shore, that orange sky, those lakes of liquid hydrocarbons extending to the horizon. Let the strangeness and familiarity both settle into your consciousness, reminding you that the universe contains wonders beyond our everyday experience, that nature's creativity exceeds our imagination, that even in the cold outer reaches of our solar system, dynamic worlds await our exploration and understanding. Sleep peacefully, dream deeply, and let your mind wander to distant shores.